Now let us learn a new term called conjecture. A conjecture is something that has not yet been proven to be true or false. But in most of the cases, it is assumed that these conjectures appear to be true. So we will use these conjectures in proving other theorems. But the conjecture itself has not been proved. So that is the meaning of a conjecture. There are many famous conjectures in the science of mathematics that have not yet been proved. For example, there is a conjecture called Beal's conjecture, and it states that if a power x plus b power y is equal to c power z, and a, b, c, x, y, z are all positive integers, where x, comma y, comma z are greater than 2, then a, b, and c will have a common prime factor. So, if you look at this, this is a statement that has been made by Beale based on his observations, but there is no proof for this statement. But this statement appears to be true because let's take some examples. 3 power 3 plus 6 power 3 is equal to 3 power 5. So this statement is true, and if you observe, A, B, C all have a prime factor 3 in common. Similarly, 7 power 3 plus 7 power 4 is equal to 14 power 3. Again, if you observe, A, B, C have a prime factor 7 in common. So if you find any such equation which is true, then those bases will always have a prime factor in common. But there is no valid proof for this. So these are called conjectures. So now let's try to prove the Pythagoras theorem. Construct two squares, a green and a blue as shown here, and let the side of the inner square be C, and the sides of the green triangles formed by this figure be A and B, and the hypotenuse be C. So you can calculate the area of the inner square by taking the whole figure and subtracting out the triangles, and that will give you the area of the inner square. We know that the area of the square is side square. So in order to calculate c square, we need to calculate the area of the total green square, which is of side a plus b, which is a plus b whole square. And you have four triangles, right angle triangles, whose sides are a and b. 4 times the area of a right angle triangle is half AB. So this would be a square plus b square plus 2ab minus 2ab. So 2ab cancels out and you will be remained with a square plus b square. So you have proven that the square of the hypotenuse of a right angle triangle, over here is C, is equal to the sum of the squares of the other two sides of the triangle, and here it is a and b. So c square equal to a square plus b square. Hence this conjecture has a valid proof, and hence it is a theorem. Now let's learn some Euclid's propositions. Propositions are nothing but theorems. So the first proposition that Euclid gave the world is to construct an equilateral triangle on a given finite straight line. So what he means by this is, like, if you are given a finite straight line, you can always construct an equilateral triangle on that straight line. So let's try to prove this. Based on Euclid's first postulate, to draw a straight line from a point to any point. So let us draw a straight line AB of finite length. Next, we will apply Euclid's third postulate, which is to describe a circle with any center and radius. So what Euclid meant by that was, if you are given a center and a distance, you can always construct a circle with that distance as the radius. So here let's assume that center to be A and the distance to be AB, and draw a circle. So by applying Euclid's third postulate, we have now drawn a circle. Again, let's apply the third postulate and draw a circle, another circle with the center as B and the radius as BA. Let the point of intersection of these circles be C. Let's join AC and BC. So now we have a triangle over here. Let's look at the properties of these sides of the triangle. We know that from circle 1, AB is the radius, and we also have another line AC, which is also the radius of the circle. So if two things are equal to the same thing, then those two things are equal to one another. That is one of Euclid's axiom. So here AC and AB are both equal to the radius of the circle, which means AC and AB are equal. So by applying Euclid's axiom, we have derived this equation. Similarly, let's apply the same axiom to the second circle. Over here we have two lines AB and BC. Again, AB and BC are the radius of the second circle. So applying Euclid's axiom, we can say that AB is equal to BC. Now if you observe, what you are seeing here is AC is equal to AB and BC is equal to AB. So two things are equal to the same thing. So applying Euclid's axiom one more time, we can say AC is equal to BC. So pretty much AC is equal to BC and AB is equal to AC and AB is also equal to BC. So all these three sides are equal. So we have constructed an equilateral triangle on a given line segment AB of finite length. So this way, applying Euclid's axioms and postulates, we can prove this theorem or proposition. Let's try to look at the second proposition of Euclid. The second proposition of Euclid states that to place a straight line equal to a given straight line with one end at a given point. What he means by this is if you are given a line segment BC of finite length and a point A, you can draw a straight line from A which has the same length as BC. So let's try to prove this. Applying Euclid's first postulate, to draw a straight line from point to point, we have drawn a line BC. And let's assume there is a point A. So the theorem states that you can draw a line from A which has equal length to BC. So in order to prove that, first let's join AB. Applying Euclid's first proposition, which is if given a line segment of finite length AB, you can draw an equilateral triangle. So now we have drawn an equilateral triangle ABD by applying Euclid's first proposition. Next, we will produce straight lines AE and BF, which are in straight line with DA and DB. So this is Euclid's second postulate, which is to produce a finite straight line continuously in a straight line. That's Euclid's second postulate. So applying that, let's draw two new lines. And let's call them AE and BF. Now applying Euclid's third postulate, which is to describe a circle with center and a given distance. Let's draw a circle with B as the center and BC as the radius. And let's call this point G. And let's call this H. So you have described a circle CGH with center B and radius BC. Similarly, apply the third postulate one more time and let's draw a circle with D as the center and DG as the radius. And let's call this circle LKG. Since the point B is the center of the green circle and BC is the radius, BG is also the radius. Applying Euclid's axiom, if two things are equal to the same thing, then those two things are equal to one another. So BC and BG are equal to the radius of the circle. So BC and BG are equal. Again, same thing, applying it to the bigger circle, DL and dg are the radius, so they are equal. And we know from the equilateral triangle that dA is equal to dB. So dl is nothing but dA plus AL, and dg is equal to dB plus BG. So dl minus dA is equal to AL, and dg minus dB is equal to BG. And dA and dB are equal. So when you subtract the same from equals, the remainder is also the same. That's Euclid's axiom. So AL is equal to BG. But we know that BG is equal to BC. So again, applying Euclid's axiom, if two things are equal to the same thing, then those two things are equal to one another. AL is equal to BC. So now we have drawn a line segment AL whose length is equal to BC with A as one of its endpoint. So that's Euclid's second proposition.